Yeah, so let's get started. Uh, I have shared the screen. This thing is visible, so I think there is not a problem. Okay, so today again we are discussing about various welding processes. Because the reason is look at the syllabus for this 11th week uh, syllabus for the course, you'll realize that there was a lengthy discussion or detailed discussion on this thing, residual stresses, uh, this various methods to control those stresses, because residual stresses are not good, because one of the important thing is that uh, corrosion, that grain boundary corrosion or something like that it is called. You can revise in your class notes and all those things. But the problem is, because of that corrosion arising due to the residual stresses, even ductile materials sometimes can fail, like brittle materials, which is called as brittle fracture, and that's not a good thing, because we have discussed this previously also. When something is some ductile material is expanding, or it is getting stretched or something like that under the action of load, various kinds of loads, you will have some time to react. Okay, but when brittle materials do uh, deform, it's not like you'll have elastic, plastic, those kind of regions distinctly visible, and it's a sudden failure. So that's why you don't. I mean, nobody wants that kind of thing to happen. Okay, so that's why many a times these residual stresses are um relieved by following different methods. Okay, so uh, apart from that, you know, uh, because of this residual stresses, there can be variation in your first of all physical appearance of your welded joint, as well as the properties. You know, so that's why these are not good in general. And you must have seen in the class that in the weld pool there is compressive stress field, whereas in the other body, apart from the weld pool or the welded region, you will have compression forces, etc. So those things are there. And then sometimes there are some techniques like brittle core, photo stress, strain gauge, to detect the residual stresses. But practically speaking, this strain gauge method is widely used. Other things are there, but very limited application, because these are not that easy to do. So then you have some methods to reduce the stress, like pinning, vibration, thermal treatment, thermochemical treatment, various building procedures and sequences. Those things were discussed in the class, so I'm not going to again discuss them. And apart from that, then there was discussion on welding distortion. So, it can, this welding distortion can happen because of material properties, as well as the procedure that was followed during the welding process. Okay, so it's not only, I mean, the welding distortion is not only the reason is not only the material properties, but the procedure parameters, operating parameters during the welding, etc., are also contributing factors. Okay, so you have to remember this different type of shrinkages: longitudinal, transverse, angular, uh, then longitudinal distortion, which is also called as bowing or bending, rotational distortion, buckling, and twisting. Okay, so this was also discussed by professor in the class in detail. So I'm just giving you the broad idea about it, because today I'm thinking we'll discuss something else apart from the studied or the told this thing. Okay, so then there was a discussion on how to control this welding distortion. So there are various methods depending on what type of material, the dimensions of material, the welding process that you want to use. All those things you have to consider in order to have least residual stresses. It is very difficult to eliminate residual stresses, but you can uh, reduce them while doing welding. And if it is not possible to do that during welding process, you can do heat treatment afterwards, which is called as post heat treatment. Okay, so those things are there. So some methods that are used for controlling distortion in welds are least root, proper tack, narrow groove, and least metal deposition. And then there are direction of welding, welding sequence, backstep welding, counter setup. All those things are there, and they were discussed also. But the idea is it's not a straightforward. So you cannot say we'll use this method in such this case and like that. It's a experienced or well-educated guess or well-educated decision that you have to take how to relieve the stresses using different methods that you are at your disposal. Okay, so then in the end there was discussion on preheat and post-weld heat treatment of welded joints. As the name suggests, preheating. So preheating basically, we'll talk about this later also, maybe today in our class also towards the end or something like that. Because in some materials, especially like cast iron or something, these kind of things become important. That whether you preheat the material before welding or do you post heat after the welding. Okay, so for some materials it's very critical. For some materials it may not be that critical, but it is one of the important parameters to consider. Okay. Then apart from that, one second. Yeah, voice is also recording. I don't know why, but I just had a doubt. Okay, so yeah, so basically when you do preheating, you control or you are not suddenly trying to melt the material. Okay, because that will have very high heating rates. Okay, sometimes those also cause problem. And in some cases those surface reactants like or surface coatings like grease, oil, scales, etc., they get removed when you preheat. Okay. And sometimes like this, it will, when you preheat the welding zone and then do the welding, in that case you give sufficient time for hydrogen to diffuse out of the weld pool, and that reduces some welding defects called as this hydrogen porosity, etc. We'll see some of the defects also, maybe not today's class, maybe next class. Okay, so there are some peculiar welding defects that are observed, so we'll see those also. And then there were various preheating methods, and depending on the material, for example, like if it's a low carbon steel, then you need lower temperatures. If it is a medium, or as the carbon content of steel increases, its hardness increases. So therefore, when you want to preheat also, the temperature up to which you need to heat, they also increase. Okay. So apart from that, then there are some post weld. Those things are there. Post weld is basically like any normal heat treatment, like annealing, tempering. Those things are there that we did, right. We studied previously. Those are under the post weld category, because once the weld is solidified, uh, we treat that as a single component for heat treatment, and that's, I mean, it is called here as a post weld heat treatment, but in general it's a heat treatment only, so nothing special there. It's just that you have to be careful what type of uh, like method or what type of temperatures you need to achieve, all those things, what type of cooling rates, because post welding, if you have various cooling rates, your grain structure that you will finally receive or obtain in your welded product, which includes weld bead also, as well as the the other parts, I mean apart from the weld bead. So all those things depending on heat affected zone, those things will change. So various considerations are there, but these things are already discussed in the class, and you can always uh, go online and search for more if you want to learn, in this topic. But so what I thought today is, anyway, there are not new, I mean, there are not many numericals from these kind of discussions that we can do. Some of the numericals we did it in the last class, so those are like mostly asked, at least in GATE exam, for as far as numericals are concerned, for from welding topic. Okay. Today also we'll try to do some numericals if possible. I mean, if they come across. Otherwise, mostly today what I'm thinking of doing is, we'll discuss different types of these things, welding methods, because in the class, I think in this course it is expected from you that you know every welding technique beforehand, and then the discussion starts after that. But I wonder, or I guess not many will know some peculiar things about different welding welding techniques. So we'll briefly cover those, and if some numericals are there in between, we'll do that. Or otherwise, you know, uh, I'll tell you the many, or the not many. I'll tell you the important characteristics or important applications in which various methods are used. Okay. So last class we stopped at the nomenclature of electrodes. Okay, and it was a 6-part nomenclature, so you can keep that in mind, because in some competitive exams they directly ask these kind of things, and if you don't know, then you can't guess also. Okay, so let's talk about various welding techniques, not in detail, because if you do that it will take a lot of time, but the objective here is, to uh, at least get you, maybe it is kind of a revision if you have studied these techniques in your undergrad somewhere. If not, or if you have forgotten completely, or if you are out of touch, then these things will, today's discussion on various welding techniques should jog your memory up. That is the objective here. Okay. Yeah. Yeah. So let's talk about some uh, various welding methods. Okay. So that is a broad topic for today's discussion, because we saw the classification earlier during the initial discussions in welding. So let's uh, talk about some of these important methods. So first category will be shielded gas welding technique. Okay. So as the name suggests, the shield means it will be, the welding tool will be shielded by some inert gas or something like that, so that it does not directly comes into the contact with ambient, and that eliminates or reduces the contamination of weld pool due to oxides, as well as it keeps heat in the weld pool for longer time. So basically, heat loss from the weld pool to the ambient is reduced. And gas means, you will have, I mean, this is shielded gas, so there will be gas shielding, and then there is welding. Okay. So first technique under this category is tungsten inert gas welding. Okay, so this is a famous welding technique, tungsten inert gas. So this is also called as TIG in common parlance. So TIG welding. Okay, or it is also called as gas tungsten arc welding. Okay, so gas tungsten arc welding. So in some questions or in some books, you will see this acronym GTAW. Okay, so they are talking about one and the same thing. Okay, so TIG or GTAW. Okay, so I'll just draw a simple schematic so that you understand what this technique is about. I mean, there are details about it that we'll discuss, but usually what happens, you'll have a workpiece like this, on which it's not like always a single workpiece. Not necessary. There can be two work pieces, and they'll have some you know uh, surface preparation like this, and this weld pool will be forming there. So in these cases, what happens, you will have your electrode. Okay, so mostly this tungsten electrode is there, because as the name suggests, it's a tungsten method, right? So you'll have a tungsten electrode. Let's assume it like this, and it will be covered. Okay, so it will be shielded. So your weld pool will be shielded like this, and you know in this region, maybe like this. So there will be supply of inert gas from a separate cylinder. Okay, so it can be outside also electrode, not necessary. Okay, so here you'll have uh, inert gas supply. Okay, so inert gas are typically helium or argon or neon, whichever is cheaply available, that can be used. Up to it should be pure. Okay, so then you have this power supply. So you can have power supply here. So this is a typical setup, and many a times this tungsten or TIG is high temperature uh, method. So therefore, the electrode temperatures typically go significantly higher. So you have this cooling water also, or cooling jacket kind of thing, which covers your electrode, and it tries to cool it down. Okay. So this is your tungsten electrode. Okay, and that's why the name. And we all know that melting point of tungsten is significantly higher. So therefore, this kind of method is used when you need higher temperatures. Okay, and in some cases you need filler also. Okay, so depending on the thickness of the weld pool, so if you have a larger thickness, you can have filler materials also. So what happens, in when this arc is formed, this filler material gets melted, and then it will go into this weld pool, and this is how you can have a shielded gas welding with tungsten electrode. This tungsten electrode is a non-consumable electrode, right? Because we are using filler for that purpose. So this is a non-consumable electrode. That is also asked sometimes, that in TIG what kind of electrode is used, because many students may not know what is TIG. So therefore, these kind of things are there. Okay, so then some important points regarding this. Uh, now the question is about the polarity, because we saw in the last class that there are different, DCSP, DCRP, AC. So what kind of power supply do you need, or what kind of power supply is preferred? So what happens here? You don't want more heat at the electrode, because you know uh, that way you need to provide more cooling water. So usually we supply AC. So some bullet points about this TIG welding is usually AC power source is preferred. Okay, so that way there will be not more, like more heating electrode, or not, neither on the workpiece. So what happens, there is something called as cathodic cleaning. Okay, so what happens, cathodic cleaning is a phenomenon in which, as the name suggests, cathode. So uh, cathodic cleaning is a process in which your cathode, if there are any oxide formations on your cathode or any scale formations, these things go away. Okay, so you know so this is nothing but a removal of oxides from cathode. So cathode is typically uh, positive, right? Anode is negative, no? So cathode. Okay. So cathodic cleaning is removal of oxides from the surface, from the cathode surface due to high energy electron transfer from anode. Okay, so basically what happens, electrons bombard on cathode, and if there are any oxide formations, etc., they usually tend to get cleaned because of this. So when you use AC power source, you get with AC power source cathodic cleaning of workpiece is also. Anyway, you have inert gas shield, so there is a less chance of uh, this surface oxides formation. But even if they do form, then if you use AC power source, usually you'll not face any surface oxides or contamination of weld pool due to oxides. Okay, so uh, this filler material, it is not always used, as I said earlier. So if the thickness is, weld thickness, if it is greater than 5 mm, you need to use fillers. Otherwise, you just do the welding without fillers also. So this is anyway arc welding. So the working principle is same, that you apply high voltage between electrode and the workpiece, and there is a very small air gap, so there will be formation of arc. And if you maintain certain optimum arc length, the arc will be sustained. And then because of higher temperatures in this region, uh, there will be melting of metal, as long as its melting point is below the arc temperature or the temperature during welding. But tungsten has very high melting point, so it usually doesn't melt, so it's a non-consumable electrode. uh, you know uh, Non-consumable electrodes are not only tungsten. uh, Nowadays you can use this graphite also. Okay, so graphite also can be used as non-consumable electrode, not in this technique, but in other techniques you can see that graphite is also non-consumable. Okay, so and one more point about this TIG is applications. So it's a first of all, it's a costly process, because you have to supply cooling water, you have to supply inert gas, you have to use tungsten. That's also not cheap. And fillers is additional thing. So those things are there. So it's a costly process, and used for welding of aluminium or magnesium alloys in various industries. Okay, so industries could be aerospace, automobile, chemical, etc., etc. But it's a costly process. Okay, it's not that widely used, because you have to have a lot of investment for this. Okay, so this is about a TIG. Now there is another version of this, which is called as MIG. So it is like metal inert gas welding. Okay, so it is also called as MIG. Okay. So the only difference between TIG and MIG is, as the name also suggests, T is replaced by M. So you don't use tungsten electrodes here, and also it is called as gas metal arc welding. Gas metal arc welding. So this acronym GMO is also used in some questions. So you should know that they are talking about MIG only. Okay, so here there is a slight difference in the operating principle. So you'll have a workpiece, something like this, which is to be welded, and this will be your weld pool, and then you'll have particular power source like this maybe. Okay, and this uh, inert gas shield is also there, it doesn't change. Okay, so again you'll have a supply of inert gas, because it is also inert gas welding, right? So inert gas shield has to be there around the weld pool. But here the difference is you'll not have tungsten electrode, you'll have a consumable metal electrode. Okay, so this is your so there will be some spool like this. So this is the difference. So you have consumable uh, metal electrode. Okay, and that's why the name MIG. And these wheels they control the feed rate. Okay. So wheels to control the feed rate. Okay, and then uh, you can connect this power supply like this, so that you'll have a closed circuit. So this is the whole idea about this. Okay, so the working principle remains same as compared to TIG, but here the only difference is there will be consumable electrode. Okay, so some of the pointers that you can have is you can use AC power source, because as I said earlier, it will have cathodic cleaning as well as not a lot of heat generation on the electrode. But since you want your consumable electrode to melt, you can use DCRP also. Okay, so direct current reverse polarity, because in that case there will be more heat generation on the electrode, which is beneficial in this case. Okay, so depending on the feed rate, so you can have faster welding rates are possible. So you can control this by controlling the feed rate using this rollers and power supply current or voltage, whatever it is. So that you can do, and you can have a faster rate of welding. Okay, so if it is, there are two things that come then. If it is if for a particular current and voltage setting, there can be drop wise, uh, this thing, drop wise melting of metal electrode. Okay, or there can be spray also, spray melting. So as you can understand, when you have high current and high feed rates, this metal will be immediately melting, and then it will be like a spray. Okay, so from electrode to workpiece, it can sometime be transferred like uh, spray. Okay, so that depends on how much current you are using. Okay, and here the advantage is you don't need to use separate filler. So no separate filler, as well as no cooling water required. Okay, so this is the advantage as compared to the TIG. Okay, so these are also used for I mean, you cannot go as high as TIG, the temperature wise, but these are also used for welding of aluminium, magnesium, copper, these kind of low melting alloys, or this pure materials also. So as long as you don't have like a high carbon steel or something like that, you can use TIG MIG. Doesn't matter. So here it can be called as jet also sometimes. Okay. So here you'll have low current. Here you'll have high current. I represents current. So depending on that, you'll have different mechanism of liquid metal transfer from electrode to the weld pool. Okay, and as it is a consumable electrode, you can use it for uh, you know uh, higher thicknesses also. So can be suitable for workpiece with higher thickness, and higher by that we mean typically greater than 5 mm. In TIG and all, you have to be careful because then you have to use filler, and you have to make sure that that filler melts, because when you have thicker materials, you need more welding deposition rate, right? So those things are there. Then in this category there is third technique, which is called as plasma arc welding. Okay, so this is plasma arc welding, or you can call it as POW. Okay, so here it's like similar to tungsten or TIG welding, but there is a difference that you supply high pressure plasma through the ceramic nozzle. Okay, so you don't have a normal arc here; you have plasma arc. Okay, so the setup, it will look something like this. You can always look the exact drawings on the internet or any standard textbook. I'm just giving you the main pointers, okay, because this was not discussed in the class, but you should know. Okay. So here you will have some arrangement like this. Okay, and here you will have your plasma arc, and on top of that you have this uh, tungsten electrode. Here also it is non-consumable tungsten electrode. Okay, like this, and this circuit is as usual. Okay, something like this. But here you don't just put inert gas and do the electric arc welding like we saw previously. You here have a ceramic nozzle around uh, this guy, like this maybe. So this is a ceramic nozzle. Okay, so my drawing is not that good in this case, but you understand, right? It's a nozzle like this. So this is your tungsten electrode, and this is your ceramic nozzle, and here you supply plasma. So maybe I'll use other color. So you supply plasma through this nozzle, and then you know there will be, like, since it's a nozzle, there will be bottom opening somewhere, not clearly seen here in this diagram, but uh, you know so that what happens, this plasma comes into the arc, and then it's a uh, plasma arc welding. Okay? And here you supply inert gas also, so that your weld pool or your arc is shielded. Okay, so this is your uh, plasma arc welding. So This is called as plasma arc. This is not a normal arc. Okay, so this is the broad setup for this kind of technique. Now the only difference that you see here is plasma, right? So what is plasma? So there are different techniques to generate plasma, but in a nutshell, plasma is nothing but ionized gas. So whatever air or gas that you have, you basically ionize it by bombardment of electrons. Okay, so there are different plasma creation techniques also. So that's not the part of this discussion, but it is essentially ionized gas or air, and that usually happens at higher temperatures. Okay, so therefore this plasma arc welding, etc. You can, with plasma you can generate higher temperatures. Okay, so of the order of 11,000 or something like that. And as the temperatures are significantly higher, you will need cooling water here in this ceramic nozzle. Okay, so this is similar to TIG. Okay, this method actually kind of is like a TIG only, but here the only difference is you use plasma, and by using plasma the advantage that you get is higher temperatures in plasma arc. Okay, so like approximately 11,000 degrees Celsius. Okay, so that's the advantage that it gives, because this nozzle, because of nozzle you'll have high velocity plasma. Okay, so because of that you can have depth of penetration more. Okay, so more depth of penetration you can achieve. Okay, so those things are there, and it's a costly technique obviously, because it's even costlier than TIG, because you need additional plasma, etc. But this technique is used in some special cases, because it's not that uh, general. So the important applications for this technique, apart from whatever we discussed, is welding of high temperature, high melting point temperature, welding of high melting point temperature materials like titanium, nickel, cobalt, molybdenum, okay, etc. etc. in jet engines. So these are some peculiar applications: jet engines or turbine blades. Okay, so these are very high application. I mean, very high temperature applications. And depending on the thickness, you can use filler or you cannot use filler. That is up to you. Okay, so it's like same with TIG. So if the thickness is greater than, let's say, 5 mm, you use fillers also. So that is possible here. Okay. So this is about plasma. So uh, plasma arc welding is not a simple, I mean, it's like upgraded or upgraded TIG, upgraded TIG for higher temperatures. Like that, you also you can remember. But yeah, for particular applications which cannot be easily catered by other shielded gas techniques, you can use plasma arc technique. Obviously, it will be costly. It's not because it's even even uh, complicated than the TIG. Okay, so this is about plasma POW. Then you have submerged arc welding. submerged arc welding. This is called as SAW. SAW. So these acronyms are also important in these discussions, because many times they use acronyms also. Just a second. Okay. So submerged arc welding, uh, the basic principle is same only. Uh, Here the difference that comes is that you don't have inert gas here. What you do, you basically put some solid flux in the consumable electrode nozzle. Okay, so you can. So for example, it will look something like this. So if you have you know uh, weld pool like this, okay, something like this, then you'll have your cone like this. Okay, so this is your cone or inert gas kind of nozzle, but it does not have inert gas. What it has is a consumable electrode. So consumable electrode like this with some spool or something, and again you'll have a power supply. So basically this will be your workpiece, right? So let's say it is something like this. Okay. Okay, so something like this. Mm, yeah. So what they do, and then you connect some power source between these two. So here you'll have solid flux. So you will not be able to see the arc. Okay, so it will be submerged. So like that. So you will not be able to see the weld pool also. Okay, so it will be submerged, the whole weld pool itself. Okay, so that is the difference in this case, and this will be your direction of welding. So you have this solid flux. Okay, so this red color. Oh, one second. Yeah. So this red color uh, thing represents solid flux, which can be some materials like calcium oxide or this calcium fluorides. Okay. So this is why it is called as submerged arc welding, because you'll not able to see the arc from your naked eye because it is submerged in the solid flux. Okay, so then there are some advantages and some disadvantages for these kind of techniques. Uh, First of all, the advantages, since you don't have direct contact with the uh, atmosphere, so it will be the arc is covered from the atmosphere. So uh, therefore the heat transfer losses as arc is submerged in flux, heat transfer or heat transfer losses from the arc are minimum. Okay, so here you don't provide uh, inert gas separately. That also is one of the advantage, that you don't need to rely on inert gas supply. Okay, so and this is your consumable electrode. Okay, so that's again acting as filler. Okay, so you don't need to supply inert gas and filler or cooling water, anything like that. You just have to supply solid flux here. Okay, so usually that flux will be put throughout this weld pool. Okay, I'm not showing it fully, but you can think of it like that. Okay, so since there are less heat losses, heat transfer losses from the arc, more heat concentration on workpiece. So that is a good thing, right? So you'll have higher welding or melting efficiency, whatever you want to call it. Okay, so it's a high. It increases the efficiency of your welding process. Okay, and also what happens? We choose this solid flux in such a way that if you look at your weld pool, you'll have uh, liquid metal like this. Okay, and then you'll have solid flux covering like this. Okay, and you choose this solid flux in such a way that the slag that is formed after the interaction with the weld pool, it is lighter than the flux. So what happens? Then you will have this slag formation on top of the solid flux. Okay. So that is where the choice of solid flux come into picture, and because of this, minimum or minimal chances of slag inclusion. Okay, so you basically uh, avoid many of the welding defects because of this. Okay. So slag and liquid metal usually don't mix because of the separating layer of solid flux. Okay, so therefore you'll have lesser welding defects, etc. Also, because of this covering, you'll have lesser splashing of liquid metal. So that is, that there is one defect which is called as weld spatter. So uh, that will be less weld spatter. Okay, so uh, these are some of the advantages. One more advantage is, you can have uh, high welding speed and high welding speed plus high deposition rates are possible. Okay, because here uh, you don't have those limitations. Okay, but you know there are some disadvantages, such as it cannot be used for all sorts of positions, because if you are using it, like, let's say, to do the overhead welding, the flux will fall down, no? So this is only suitable for positions. Flat in the sense, the flux, I mean, it should not fall down or like that. It should have some stable structure, and you know only single pass you can do, because if you want to do multi-pass welding, it is not possible here because it is covered with the flux all the way. So if you go back, you will include slag and all those things in the weld pool. And another disadvantage is that this heat affected zone is larger, and therefore post heat treatment is required. So that also is a drawback. Okay, but this is a very important technique, and there are certain applications that you should remember that are catered by this technique, such as you know, or applications, I should say. Uh, Joining of high thickness plates in ships. Okay. And fabrication of pressure vessels. Fabrication of pressure vessels, or even our gas cylinders that you or that we typically use in our homes. So those are made by this one. And structural stresses. Okay, so these all things are usually made by submerged arc welding. So this is very important, one of the important ones. Okay, so this is about arc welding techniques. Then let's talk about some of the uh, gas welding techniques. Okay, so this chemical reaction based welding techniques, because this oxyacetylene torch and all those things are widely used, and you must have seen by now at least sometimes somewhere. How do they do the oxyacetylene welding? So 1 second. Yeah. So let's talk about chemical reaction based weldings. And one of the important ones amongst this category is the gas welding. So this is basically using the oxyacetylene torch or flame. Okay. So many a times it is also called as oxyacetylene welding or oxyacetylene torch welding. Okay, so these are all the names they are used. Okay. So here you can you can just see that you'll have two gas cylinders like this. One will be supplying oxygen because for generating flames, basically you are doing combustion and you need oxygen. So there is one oxygen cylinder like this. So this will be your oxygen cylinder. Typically it is at higher pressures like 15 megapascal or something, or 150 bar or something. Sorry. And then you'll have another cylinder of oxyacetylene, acetylene basically, not oxyacetylene. Okay, so okay. And they go to this combustion chamber basically, which is nothing but the torch that is typically held in the hands of the welder. Okay, and then at the end you'll have some nozzle kind of thing. Okay, and then your workpiece will be there. So here you will have a flame. Okay, so basically you have flame like this, and then you put some filler material which melts, and then you have welding. Okay, so this will be your acetylene cylinder. Usually it is at lower pressures because uh, this acetylene is a highly flammable gas, and if you keep the cylinder at very high pressures, there can be chance of explosions or something like that. Okay, so this is basically how this whole technique looks like. Okay, so basically what I mean here is this flame is actually initially externally ignited. Okay, so this flame is ignited externally initially, and then slowly, I mean not slowly, once it is ignited, it will sustain based on the gas mixture that you used of oxygen and acetylene. Okay, so there are two types of reactions that occur. One is called as primary reaction. So, in this nozzle or torch, there are two types of reactions that occur. First is called as primary reaction. So that is acetylene mixes with oxygen and it gives you carbon monoxide. Okay, and some exothermic reaction takes place, and there will be some hydrogen also. And then you'll have secondary reaction, in which this carbon oxide plus hydrogen mixture again reacts with some oxygen, and you get 2CO2 plus H2O plus delta H2. Okay, so this complete reaction, or this is a stoichiometric reaction. Okay, so in this case you use 1 mole of acetylene gas and then total 2.5 moles of oxygen gas, and you get CO2 plus water vapor and some delta H. So typically it is equal to delta H1 plus delta H2. Okay, so this is the heat that you get out of this combustion reaction, and that is what is used to melt the filler. Okay, so here one thing is that this delta H2 is typically higher than delta H1. Okay, so this is the observation, because we see some things about that later. Okay, so first thing that you should note here is this 2.5 CO2. If you pay attention, it is mixture. It is summation of 1 from primary and 1.5 from secondary, right? So this comes from uh, oxygen cylinder that we have here. Okay, oxygen cylinder, whereas this 1.5 moles of oxygen comes from atmosphere. Okay, because this secondary reaction typically takes place such that oxygen from the atmosphere is available in the surroundings, and that's why. So you don't supply the whole 2.5 moles of oxygen. You only supply 1 mole of oxygen gas from cylinder. Okay, so this is very important. Many times students think that all of the oxygen that is required for the reaction or combustion is supplied from the oxygen cylinder. It's not like that. Like it is 1:3. So basically 40% only we supply from this thing, uh, only 40%. 40% gas from cylinder, oxygen gas, 60% we take from atmosphere. Okay, so then there are different types of flames that you see. So this flame, depending on, you usually have some controls. Okay, it's not like that you just mix them. You usually have some balls, etc., so that you can control the flow rates of acetylene and oxygen that mix in the nozzle. So there are different types of flames that you can get. First is called as neutral flame. Okay, so in neutral flame, uh, you basically use oxygen and this C2H2 gas 1:1. Okay, so this is about this thing. Okay, this gas is from the oxygen cylinder. Okay, not total oxygen. So basically, you should think about this reaction. Okay, so in this reaction, you use 1:1, and you typically 1 second. We typically use from nozzle. You'll see some flame like this, not exactly like this, but you know this temperature will be around 3200 degrees Celsius, whereas on the periphery you will get around 1275 degrees Celsius. Okay, and then there is a 1 second. Yeah, 1 second. So this neutral flame, it makes hissing sound. Okay. And it is used for, it is a general purpose flame used for general purpose welding of mild steel MS, low carbon steel, then aluminum alloys, and cast iron. Okay, so cast iron, this also sometimes they ask some questions like that. Okay, so this is about a neutral flame. Okay, then you have second flame, which is called as oxidizing flame. Okay, so as the name suggests, it's oxidizing flame, right? So you'll have more of oxygen here. So here the ratio of O2 to C2H2 molar ratio is typically 1.15 to 1.5. So you use more oxygen. Okay, so in that case, what happens? You basically get slightly higher temperatures in your flames. Okay, so here, you may get around 3300 degrees Celsius, and outer it depends. Okay, so around, but you'll get slightly higher, or maybe approximately 1300 degrees Celsius, like that. Okay, so uh, this oxidizing flames make roaring sound. So you'll have higher intensity sound when you have oxidizing flames. And what happens? These oxidizing flames are used for higher temperatures. Okay. 1 second. Yeah, so this cast iron that we were talking about. So what happens? This, you know, because of this torch, you know, there is this inner flame which is at 3200 degrees Celsius. But this flame, in general, what happens when you have cast iron? This torch usually uh, preheating and post heating takes place. Okay, so as you remember, in cast iron you have flaky graphite structures, right? So that's prone to fracture, and you cannot directly just do the welding on cast iron. You have to preheat, because you have to. Otherwise, if cooling rates are very high, there will be fracture. Sorry, heating rates as well as cooling rates. Okay, so therefore, since I mean for welding of cast iron, you need preheating and post heating. Okay, so therefore, uh, this flame, apart from doing welding, it also preheats and post heats. So that's the reason why uh, we can do cast iron welding using this oxyacetylene flames also. And here you can do the welding of uh, copper, zinc, brass. And then you have the third category of flame, which is called as carburizing flame. Okay. So basically in all these flames what happens, this 3200, 3300, this is the region where your primary reaction takes place, and then towards outer side you get the secondary reaction, right? And that's where you use atmospheric oxygen, that 60% from the atmosphere. Okay. So then you have carburizing flame, but this carburizing flame, it has a slightly different appearance. Okay. So for all the flames, this inner part is white. Okay. Okay, maybe I'll write it here somewhere. So for all flames, inner part or inner part or primary reaction part is white. Okay, and outer part or secondary reaction part is blue in color. Okay, but in carburizing, what happens? You choose higher content of your this thing, uh, acetylene. So in that case, your O2 is to C2H2 concentration, molar concentration is 0.85 to 0.95, and therefore, you know, you see a third kind of flame. So after nozzle, this is usual flame, but you'll see another flame like this inside. Okay, so here you'll have temperatures like 2900 degrees Celsius. But the peculiar thing that is uh, observed here is this intermediate flame. So this is intermediate flame. This is not observed in other cases, okay, and it is in red in color, okay, and it makes no sound. When you have carburizing flame, you will not have any significant sound. It's very quiet, and this length of this red flame is directly proportional to the unburned C2H2. So if you have uh, more of a C2H2 concentration, then the red color flame will be longer. Okay. And here basically, this one point I missed. It is oxidizing flame is used for carbon sets, this copper, brass, etc. because oxides are lighter. Okay, so for these materials, oxides are lighter and they typically float. So because in oxidizing flame you have a high chance of oxidation, right? So for these metals, it doesn't matter because oxides are lighter and they basically float. Okay, so that's why they are used for that. And this carburizing flame used for high carbon steel and nickel alloys, etc. So basically, for harder materials, temperatures having so materials having high carbon contents or high melting point materials, you use carburizing flames because because of this carburizing flame, there is a chance of increase of carbon percentage. Okay, so you cannot use it for MS or low carbon steels. But in high carbon steels, there is already high carbon, so that doesn't matter when you use carburizing flame for them. Okay. So these are some of the important pointers regarding the torch. And yeah, if you have thick materials, let's say if you want to weld something which is greater than 5 mm in thickness, then you have to use fillers. Okay, so those things are there, and then you use flux also when you have fillers such as borax, etc. So those things are there, but you know these are some of the important pointers about gas welding. Okay. Then usually what they do, this C2H2 is a very risky gas. Okay, it's not that safer to handle. So they usually put some acetone in that cylinder. Okay, so uh, that acetone is sometimes absorbing the C2H2, and the pressure is remaining in the balance. So not an important question, but just so that you know that this acetone is sometimes used there. Okay, so this is about this. And then if you just use this for welding, that is fine, but many times you can use this same setup for cutting also, metal cutting. Okay, so the working principle is same, it's just that the nozzle shape they slightly change it, and you can use the same setup to cut the metals also. Along with nozzles you can cut them also. Okay, so those things are there, but since we are focused on welding, let's talk about welding only. Okay, so there is one question that you can think of, because here we have this molar ratios, etc., right? So question goes like this: uh, two copper sheets are welded by neutral flame, okay, with acetylene consumption, so C2H2 consumption of 8 liters. Okay. But the weld was defective. Then it is re-welded with oxidizing flame. Okay. So find the range of total oxygen gas consumption in these, or just total oxygen gas consumption. Okay, so this is a kind of a sample question. So we know that first they did with neutralizing flame. So in neutralizing flame you have this, first was neutral flame, molar ratio. So volumes you can directly take in the molar ratios, you cannot take mass. Okay, so therefore initially they used C2H2O 8 liters, right? So therefore you have to use 8 liters of oxygen also. Okay, that is for first. But secondly, then they are using oxidizing flame. So we know that this ratio will be equal to, I mean, it will be greater than 1 for oxidizing flames, right? So it could be anything between 1.15 to 1.5. In this question, they did not give you the ratio, but if it is asked in some exam, they may give you directly this number, so you can use that also. So in that case, this oxygen will be 1.15 or 1.5 times of 8, correct? No, because it is 8 liter. So if you calculate these numbers, it should be 9.2 to 12. Okay, so you could have used 9.2 or 12. Okay, so therefore total oxygen consumption can be 8 plus 9.2 to 12. So basically you'll have 17.2 to 20 liters. Okay, so they won't ask you data entry because it's a range here, but they will give you some options, like one option could be 15 liters, one option could be 18, one could be 22. So you have to choose the option which falls in this range. Okay, so this is the type of question that can be expected from this kind of these things. Okay, so this is about torch welding or oxyacetylene welding. There are another there is another this thing also, which is called as thermit welding. Okay, so basically here you used oxygen and acetylene combustion, right, as a heat source for melting. There you use iron oxide plus aluminium as mixture which is called as thermit mixture. So you basically heat it up to certain temperature, and then exothermic reaction takes place between those materials, and then you get the liquid iron. Okay, so we'll talk about that. So yeah, I mean, okay. So first is gas welding. Second is called as thermit welding. So sometimes they ask this also because it also has a specific applications in repair of railway tracks, etc. So you should know the basic principle. So what they do typically, uh, you know, yeah. So what they do basically, there is a mixture which is called as thermit mixture. So thermit mixture. So it has iron oxide Fe3O4 plus aluminium in the ratio of 3:1 by mass. Okay. So I mean, this is commonly used thermit mixture. You can have other oxides also, copper oxide as to aluminium, or chromium oxide as to aluminium. So these are other options, but primarily we used this iron oxides because we need molten iron for the reaction. And this reaction you can do the stoichiometry balance. So you'll get Fe3E4 plus 8Al. It will be around at 1200 degrees Celsius. This reaction takes place. You'll get 9Fe plus 4Al2O3. So this is aluminium oxide. This acts as a slag and some exothermic reaction. So this will be your liquid iron. This is your slag. So what they typically do is you basically have two plates or work pieces like this, and they will do some welded joints, etc., so that this thermit mixture will not fall down once you put it. Okay, so like that they will do some nut bolt arrangements, and then you will put this thermit mixture on some kind of crucible like this, and you basically heat up to 1200 degrees Celsius. Okay, so this is some people call it as crucible, etc. You will have thermit mixture inside depending on how much molten iron you want, and then this iron will get at 1200 degrees Celsius. Exothermic reaction starts, so you'll get even more temperatures, higher temperatures, and this liquid iron will fill here. Okay, and then on top of that you'll have Al2O3 slag. Okay, so this is how this building process takes place. So the famous application or the famous question that is asked is, first of all, what is thermit welding? And it has a peculiar application which is repairing of railway tracks, because you cannot move railway tracks, and if they have some cracks or something, you have to do the welding or repairing there only. You cannot move them, right? So this method, you take thermit where you want, and then do the melting there. So you see, so wherever you cannot move the workpiece from its original position, you have to do this. Okay, so another could be uh, another application could be large size open castings. Okay. So, I mean, these are all secondary applications, but the primary one is this railway tracks. Many interviews they ask, because when you say welding technique, I mean, if you are going into that domain during your interview, they can ask you, right, how do you weld railway tracks, cracks in the railway tracks? So thermite welding is one of the important things, because other methods you cannot do. First of all, you cannot move the tracks. Secondly, you need very high temperatures to melt the iron. Okay, so you have to be using thermite welding is the more suitable option. Okay, so then there is something called as atomic hydrogen welding, etc. But that is outdated technique. So basically, and hydrogen is not a good idea also. First of all, handling etc. is difficult, and if it is getting into the interstitial voids, that results in this hydrogen porosity, etc. Right. So nowadays, that atomic hydrogen welding is outdated, not used. So leave it. Then this resistance welding is there. So this was also discussed in the previous classes, so we are not going again into that. But just one or some pointers that I'll just dictate, so that you can refresh some things, or if some things are not discussed in the class, you'll remember them. So in resistance welding, you have spot welding, then you have beam welding, right? And apart from that, seam welding, not beam, seam welding and projection welding. Okay, so these three things are there, and this was discussed in the class. So leave it. Again, we will not do that. But here you have to be careful that uh, you apply current for very small duration, very high current, very small duration, so that heat gets generated and you will have local melting. And then you press, which is called as squeezing, and that is done using some presses or something like that. And then the solidification happens in this pressed state. So then you get nugget formation, and in case of seam, you will have like line welds. Okay, so in case of this spot welding, you cannot get leak-proof joints, and you'll have basically marks on your sheets. Okay, so this nugget marks. Whereas in seam welding, you can have leak-proof joints, and the seam welding is sometimes used in fabrication of automobile fuel tanks, radiator bodies, mufflers. In exhaust system, there are mufflers. So there you can use this beam welding, because you basically you can use these seam welding for smaller thickness. Okay, so you cannot use it for larger thickness welding, but smaller thicknesses like mufflers, radiators, fuel tanks, you can use seam welding. Okay. Then you have this projection welding. So basically, as the name suggests, it is a projection. So on one workpiece, you'll have projections, another will be not there, and then you basically that those projections uh, act like melting or initiation of melting points, because the resistances are higher there, and then you press or squeeze. Okay, so again it is again not leak proof, but it is used in many uh, simple applications, like formation of or fabrication of grills using wires, okay, or joining of threaded screws or nuts to the sheet materials. Okay, so those things, those kind of applications are there. Then this is resistance welding, right? So we are discussing various resistance weldings. So in resistance welding, there are some other categories also, uh, which is called as flash butt welding. So in this, what typically done is, the principle is same for resistance welding. That's for small time you pass very high current, and then you press. Okay, so when you press butt to butt, that is called as butt joint, and that is called as flash butt welding. Okay, so uh, those things are there. So maybe we can take one more question on this. Okay, so resistance welding category we are talking about, but not going into details because it was discussed in the previous classes by professor also, and I think I also discussed. Okay, so resistance welding. So types, right? This is spot, seam, projection, and flash butt welding. Okay. So uh, regarding this, let's take one question. Okay. So here it is mentioned that two pipes of ID 100 mm and pipe thickness 5 mm are joined by flash butt welding. Okay. With, so they have given some information of this power source, that it is a 30-volt power supply. Okay, so 30-volt power supply is there at welded area 1 mm from both pipes is melted. Okay. Contact resistance is given as 42.4 ohms. Okay. Heat required for melting is given as 64.4 megajoule per meter cube. Okay. And then they want you to calculate the time required for welding. Okay. So this is the question. So if you don't know what is flash butt welding, you'll be stuck in these kind of questions. So flash butt welding, as you know, there are two pipes. So they'll have ID and OD like this, and then you have a power source here, maybe something like this, 30-volt power source, and then you make them like you connect them and pass very high current for small duration, and then you press them. Okay. So in the end you'll have a connection like this. So this will be your weld pool. Okay. So they have said that this ID is 100 mm for both, and thickness is 5 mm. So OD will be 110 mm. Okay. So this is information given. Voltage is 30 volts, that is given. And here they mentioned that 1 mm from both, so 2 mm of this will be molten. Okay. Contact resistance, let's say R, is given as 42.4 ohms, and the heat required for melting is some joule per meter cube. So what you can do from this unit, you can have this idea, right? So volume of weld will be uh, cross sectional area into 2 mm, right? Thickness. And what will be the cross sectional area? That will be pi by 4 dO square minus di square into 2. Okay, let's calculate it in terms of mm cube, then we'll divide. So that will be pi by 4. D square will be 12100 minus 10,000. So, that is 2100, right? So this will be 2100 into 2. So let's calculate that. So basically we have to do pi into 2100 divided by 2. So you'll have 3298. Yeah, so this will be 3298.672 into this is mm cube, right? So let's convert it into the standard units. So 10 to the power minus 9 meter cube. Okay, so and what they have mentioned is heat required for melting is this. So heat required will be this 64.4 megajoule per meter cube into this 3298.672 into 10 to the power minus 9 meter cube. So meter cube gets cancelled, right? So you'll have this megajoule only. So now you have to multiply by 64.4 and divide by 10 to the power 9. Okay, so you get, and this is in megajoule, right? So basically, if you want it in terms of joule, so this is 10 to the power 6 and 10 to the power minus 3. So into basically, yeah. So you get 212. Okay, 212.434 joules. Okay, and they have not mentioned any efficiency or anything, but if they mention some efficiency, etc., so you have to multiply by that factor. So here they have not mentioned. So this has to be equal to I square RT, right? Because we are interested in time. But they have not given you I, they have given you V, voltage, right? So we know that V equal to IR, right? So I is basically, this is Ohm's law. So I is V by R. So I square RT will be V square by R square. Okay, so this RR gets cancelled. So therefore, V square T by R is 212.434. And now you can calculate. So this will be 212.434. Resistance is 42.4 and voltage is 30. So 30 square is 900. Okay, so we can calculate that. Okay, so you get the time as 0.008. So basically 10 seconds. Okay, so this is the time for this flash butt welding process. This is how you try to solve these kind of questions. Okay. Then there is a special kind of welding technique which is called as electroslag welding. Okay, so this is the combination. Actually, this is not resistance purely, not purely arc welding. It's combination of electric arc welding plus resistance welding. Okay, so this is the speciality of this technique, electroslag technique. Okay, and typically, if you look at the schematic for this, it is usually used for uh, you know filling up face-to-face joints between plates. Okay, so you'll have plates like this. Okay. And maybe another plate, so I'll just duplicate this. Okay. So you may have some arrangement like this. So yeah. So what they do, they typically put some copper plates here, and they apply consumable electrode here. Sorry. So you have a consumable electrode here, something like this. Okay, so this is a consumable electrode, and you'll have a arc welding at the start here, and therefore you need some power source, right? So you have a power source in between these guys. Okay, so this is the typical setup, and this is your consumable electrode. Okay, and what happens, and this is some copper plates to block, actually, because if you don't put copper plates, this molten thing will just go down, right? So you will not have a filling. Okay, so initially you generate arc. Okay, so initially electric arc generation between electrode and workpiece. Okay, so electric arc is used for heat generation. But then what happens when you have electric arc? You use certain flux, and then you have this slag formation. So this is the typical electric arc welding characteristic. So that slag, uh, slag will be floating on top of your electric arc. Okay, 1 second. Yeah, and then what happens as this electrode melts? So this is first thing. Then as the you know height of liquid metal increases due to short circuit, arc is extinguished. Okay, so this arc is not sustainable here. Okay, so it gets extinguished, and then this further heat generation takes place due to resistance of slag. Okay, so this slag layer, it will have some resistance, right? So what you do, once the arc gets extinguished, you supply high rate current. Okay, so this slag resistance acts as your uh, resistance in case of resistance welding. So initially it is electric arc welding, but after a point it becomes resistance welding. Okay, so this is a particular technique which is combination of electroslag, resistance and electric arc. Okay, and we should remember certain applications which are peculiar for this. Okay, so first is again uh, shipbuilding. It comes into handy because joining of high thickness plates, and this joining is edge to edge. Okay, it's not a it's not a smaller edge. Okay, it's like a surface to surface. Okay, so in ships, sorry. Okay, and apart from that, you can have fabrication of press frame. So basically the istri that you use for pressing your cloths, so that is also fabricated using this technique. And rolling mill stands, etc. So, uh, so you should remember these some of the peculiar applications. Okay, so this was about resistance welding, and this is a combo of electric plus resistance. Then there are certain more, interesting type of techniques, which comes under this autogenous welding. So basically, you don't use any of the filler material in these cases. Okay, so this is autogenous. Will have first is called as explosive welding. Then you'll have ultrasonic. Then you'll have friction welding, forge welding, diffusion welding, and then there is something called as laser beam or electronic beam weldings. So those things are there, and then finally you have brazing and soldering. So we'll see those things, maybe not today because today we are running out of time, and maybe next class, which we actually have two classes. So next class is the last class because it's a 12th week, but then you have one more revision session kind of thing is there. So we have two more classes, but I think apart from the discussion that is done in the class, which is also important, but this refresher on your basics is also important, because otherwise, you know, we may discuss high level things about weldings, etc., but you don't even remember what is TIG, what is MIG. So then it's difficult to do this, right? So next class we'll discuss some things about this autogenous, autogeneous welding techniques. Okay, so here you should remember that they don't use any filler materials. Okay, so yeah, this is like a TBD. Next class we'll do this. Okay, and I'll just note down what all comes under this category. So you'll have explosive welding. Then you have ultrasonic. Okay, so this ultrasonic welding, it also has very interesting applications. For example, the Y keys that you use, if you have noticed, it is the metal and polymer, they are welded together, right, or joined together. So that happens, or that is possible using ultrasonic welding. Friction welding, this was also done in the discussed in the previous classes, I suppose, and this is a very hot topic of research in this area. Okay, friction stir welding, friction welding, all these things. Then you have forge welding. Then you have diffusion welding. And then there are some other categories which are, electron beam welding and laser beam welding, etc., etc. So those things are there. We'll see them later. And then you have this, this is for autogenous. Then you have this solid liquid state welding. Okay, so here you have like three categories are there: brazing, soldering, and something called as braze welding. Okay, so this was discussed, I think, in one of the previous classes also. So we'll not go into this basics, etc., because you already know how they function. But still, there are certain things that you should know, and we'll talk about them. And then there are certain welding defects. Okay, so we'll talk about them also. Maybe I think next class, maybe professor also will be talking about them. I'm not sure. Okay, so and then there are some properties like weldability, etc., etc. So let's talk about them in the next class, because today we are almost at the end of our class, and if we start something like this now, and it will be not good idea to stop in between. Okay, so we'll spend some time in the next class, and we'll try to see if there are any other numericals, etc., that we can pick up. Okay, so that's it. Yeah, this was mostly theory discussion because it's the nature of topic. So let me just see your week 11 assignment, whether you'll be able to do it or not. Yeah, residual stresses. Okay, so many of the questions are residual stresses. So you should remember the property of residual stresses, because that was clearly given in one of the slides in the class lectures. Okay. Then those 6 type of distortions or shrinkages. Then why do we do preheating? Okay, so yeah, I think all of the above. Yeah, that's a tricky one. Okay, so I think you'll be able to solve your assignment questions if you just follow your class notes or class slides that are also shared. And then these today's discussion is mostly regarding clarification or refreshment of about basic welding techniques. What are they? How they function, and some pointers about them. Okay, so we'll stop here today, and we'll continue with these autogenous and all these things in the next class. Okay, so yeah, see you in the next class. Bye.